Okay. Hello, everyone. This is our recording for Psych 2216 to make up for our missed class on Thursday. So we're going to start off just by talking about what do we mean by the terms sensation and perception. And then we're going to kind of go through some steps in the sensation and perception process, that steps that are kind of universal to all of the senses, whether it be vision, hearing, taste, smell. So first, sensation and perception, what is it? Everything we feel, think, and do depends on sensation and perception. So these are important, interesting concepts, and so important and interesting that philosophers have been thinking and talking and writing about the topic of sensation and perception for over 2,000 years. So as far as the formal study, that's a little bit more recent, but certainly philosophers have been speculating on sensation and perception, the mechanisms behind these processes for quite some time. So philosophy aside, we are going to approach the study of sensation and perception from a scientific perspective, which means that we need scientific methods to study sensation and perception. And this is what we will spend most of this class discussing, this variety of methods that are used in psychology to study the senses. And then we will also, this will be the methods used to, some of the methods used to study sensation and perception will be the topic of your first lab assignment. So we'll spend most of this class, this recorded class, talking about those methods. So sensation, the ability to detect a stimulus and turn that detection into a private experience. So that private experience is going to be our perception of that stimulus. So perception involves giving meaning to that detected sensation. So one way to think about the concept of sensation and the concept of perception is that sensation is more of a physical process, whereas perception is more of a psychological process. Okay, so we've got some steps to look at in the perceptual process. So how we get from that sensation, that physical stimulus from the environment to that psychological process, the perception of it. So we're going to look at some of these the steps in the perceptual process. And like I just mentioned, these steps really apply to all of the senses. And we've got it divided up into steps kind of to make it a little bit easier to understand. But these steps are not necessarily discrete. So they're not necessarily, there's not a clear division between the steps. This is just kind of a way to kind of outline the process and make it a little bit easier to understand. Okay, step one, we've got the stimuli. So stimuli, this is going to be some type of environmental stimuli from out there in the world. And this can really be all objects in the environment that are available to the observer. So an important part of, step one is, attention, because the observer, we have to select and attend to those objects in the environment. So the stimulus coming in from the environment, that is going to impact what are called receptors. So all of our sensory systems have sense receptors that are able to detect certain types of environmental stimuli. So whether it be the photoreceptors for vision, hair cells, if you're talking about audition. So all of our senses have sense receptors that are capable of detecting certain types of environmental stimuli. So the stimulus is going to impact the receptors, and this is going to result in some neural activity that will result in an internal representation of that stimuli. Okay, so next step, transformation and representation. So the principle of transformation, when our sense receptors detect energy or stimuli from the environment, this has to be transformed. It has to be changed from the environmental stimuli into a perception. So what lands on our sensory receptors is not the same thing as what will be the final perception. So it has to be transformed. So this brings us to our next aspect of this principle of transformation and representation. So transformation has to be that environmental stimuli has to be transformed from the environmental stimuli into something that our sensory, or that something that our central nervous system can understand. So this brings us to the principle of representation. So our perceptions are only based on representations of stimuli on our sense receptors and the activity in our nervous system that results from that stimuli. So our perceptions are not based on contact with the stimuli. So this brings us to our next, let me just skip back here for a minute so our next step, excuse me, step 3 is going to be the principle of transduction by the sense receptors. So, but before we move on to this, let's come back to this idea that our perceptions are based on representations of stimuli landing on our sense receptors and the activity in the nervous system that results from it. So it's not based on contact with the actual stimuli. So just to reiterate that point before we move on to the next one. So step 3, transduction by the sense receptors. So our sense receptors, they have a very important job. And that job is to transform or convert that environmental stimuli into something that our nervous system can understand. So sensory receptors, they are specialized neurons that respond to specific types of stimuli. So when sensory information is detected by a sensory receptor, this means a sensation has occurred. So, for example, if we're talking about vision, light enters the eye. So the light is the stimuli. That is the environmental stimuli. That is the information coming in from the environment. So light enters the eye, and this causes chemical changes in the sensory receptors that line the back of the eye. So these are the rods and cones in the retina. They are the sensory receptors for vision. So when light enters the eye, it causes chemical changes in the photoreceptors and the rods and cones that line the back of the eye. So these cells in the eye that detect light, called rods and cones, and the rods and cones, they contain visual pigments that react to this light. We'll learn a lot more about the retina and the different types of cells that live there in the coming chapters. But for now, continuing with this example from vision, so when light lands on the eye, it causes chemical reactions in the retina. So these cells in the retina, the photoreceptors, the rods and cones, they relay messages to the brain in the form of action potentials. So action potentials or electrical signals are the language that the brain understands. So our brains don't understand light energy. If we're talking about audition, our brains don't understand sound waves or any other type of environmental stimuli that our sense receptors come into contact with. What the brain understands is action potentials or electrical signals. So it's the job of the sense receptors to convert stimuli from the environment into something that the brain understands, and that is action potentials. So the conversion from sensory stimulus energy into action potentials, this is known as transduction. So this is the very important job that the sense receptors do. They transduce environmental energy into neural impulses. So we'll talk more about how transduction works for each of the senses that we talk about. Okay, step 4, the neural processing. So neural processing, this is changes that occur in the brain as signals are sent from the sense receptors to the appropriate areas of the brain for whatever sense we're talking about. Okay, so what are these areas? So let's just look kind of quickly at the primary receiving areas, sensory areas of the cortex. So for vision, we've got the, let me get my cursor. We've got the occipital lobe back here. That's the primary cortical area for vision. In the parietal lobe, we've got the somatosensory cortex, which is right here. That is important for skin senses. Temporal lobe is important for hearing. So those are the key areas of the cortex involved in sensory perceiving areas. The ones for taste and smell are a little bit more difficult to see in this picture, but we'll get to those when we cover those senses at the end of the course. Okay, so let's move on to step 5. So we've got, what have we got so far? Let's just recap. Okay, so we've got step 1, we've got stimuli coming in from the environment. Step 2 has to be transformed basically into a representation. Then it has to be transduced by the sense receptors and transduced, so change from environmental stimuli to neural impulses that are going to be sent onto the respective parts of the brain for whatever sense we're talking about. Now we're on to step 5, behavioral response. So experience and action. So electrical signals are, transformed into a conscious experience. So, this is kind of the, not really the end point, but, this is the point where, those light signals are coming in and the person says, okay, that's a tree. So they perceive the object, they recognize it as being whatever object it is. In this case, they recognize it as a tree or what have you. Okay, so conscious experience of whatever we are, whatever environmental stimuli is coming in and forming the perception. That's the step 5. conscious experience of that environmental stimuli. So when we're talking about the perceptual process, there's a very important role that knowledge and previous experience plays. So while our sensory receptors are constantly collecting information from the environment, it is ultimately how we interpret that information that affects how we interact with the world. So perception refers to the way that sensory information is organized, interpreted, and consciously experienced. So perception involves both bottom-up and top-down processing. So bottom-up processing, this refers to the fact that perceptions are built from sensory input. So bottom-up processing is based on incoming stimuli from the environment. It's also sometimes called data-based processing or data-driven processing, with environmental stimuli being the data. So to think of an example of bottom-up processing, I can think about flowers in my garden right now. It's a good example for me. So my orange rose bushes, I see them, they pop out at me because of the bright color. It grabs my attention because it stands out against all the green foliage. This is bottom-up processing. Top-down processing, on the other hand, this is, how we interpret sensations based on our available knowledge, our past experiences, our thoughts. So this is top-down processing. So this is, knowledge that the perceiver is bringing to the perceptual situation. So it's based on our previous knowledge, cognitive factors as well. So to continue on with my flower example, my poppies, the poppies in my garden that were blooming last month, they've stopped blooming, but I know what they look like when they were blooming. I can imagine it. So this is top-down processing. Okay, so we've got incoming environmental stimuli being, converted into a perception, but do all sensations result in perception? So, although our perceptions are built from sensations, not all sensations will result in perception. In fact, we often don't perceive stimuli, especially we often miss incoming stimuli, especially in cases when it remains relatively constant over prolonged periods of time. So a good example that illustrates that not all sensations result in perception is a phenomenon known as sensory adaptation. So sensory adaptation is basically, it's a gradual decline in our sensitivity to a stimulus after we have experienced it for a prolonged period of time. So there's not necessarily a one-to-one mapping between sensation and our perception of those sensations. So sensory adaptation influences how we register sensory input. So sensory adaptation influences that incoming data and how we register it. So let's think of an example of this. Good example for this time of year. Imagine jumping into a pool or a lake. It is initially, maybe it's really cold, right? You jump into a lake. It's really cold at first, but if you stay in there for a few minutes, you've probably noticed that the water temperature is not as cold as when you first jumped in. In reality, the temperature stays constant. If you've been in the lake for 5 minutes, the temperature has not changed in 5 minutes. It's the same, but your sensitivity to it decreases after continuous exposure. Similar thing happens when you put your clothes on in the morning. You feel them initially, but you probably don't feel them now. So sensory adaptation, it's an automatic, built-in process that is really adaptive because it keeps us tuned to changes in sensory input rather than constants in sensory input. We don't need constant confirmation that our clothes are on. Changes are more important because they may signal threats to our safety. So sensory adaptation shows us that there's not a one-to-one mapping between sensation and perception, not a one-to-one mapping between incoming sensory input and our perception of it. And it's a behavioral adaptation that has probably been shaped by natural selection in order to benefit our survival and keep us tuned to changes in sensory input rather than constants. Okay, so now we know a little bit about sensation and perception, kind of some of the concepts within those larger ones. Now let's look at how we study sensation and perception. So at the end of the day, sensations are sensation is the very physical aspect of the perceptual process. But at the end of the day, perception is very subjective. So it's very subjective. It's very individual. So how can we measure something as subjective as perception in a scientific and reliable, objective way? Because what we're really trying to measure is the relationship between the mind and the body. So remember at the beginning of this lecture, I said that sensation and perception has been discussed and speculated on by philosophers for thousands of years, and really it's of interest to philosophers for all of these thousands of years, because what we're really talking about is the relationship between the mind and the body. So psychophysics, this is a method that that seeks to measure the relationship between the mind and the body in a scientific way. So it's this psychophysics. It's a scientific study of the quantitative relationship between physical stimuli and our psychological experience of it. So psychophysics is attempting to scientifically measure the relationship between the mind and the body. So it's a scientific way to measure the relationship between stimuli and our behavioral responses to that stimuli. So psychophysics, it's a method developed in the 1800s. Developed by a man named Gustav Fechner, who is pictured here on the slide. So the term psychophysics itself breaks down into, in terms of the meaning of the word, psychophysics. So psycho for mind, physics for matter. So literally translates into studying the relationship between the mind and matter. So the mind and the physical world. So Fechner, he was a German scientist working in the 1800s, and he thought it should be possible to describe and quantify the relationship between the mind and the body using mathematics. So he was a leader in the development of psychophysics. He and others who worked on developing and kind of developing and streamlining the method of psychophysics what the interest was here is in figuring out what the boundaries of perception were. So they wanted to know things like, what is the faintest light that can be seen? What is the quietest sound that can be heard? How much change in a stimulus is needed before we can tell that there has been a change? So these are the types of questions that psychophysics seeks to answer. So, what is the faintest light you can see? What is the faintest sound you can hear? So a good starting point for measuring the relationship between sensations and our perception of them, or our experience of them, is to measure the limits of what we can perceive. So, what is the faintest light that you can see? How would you know? What is the loudest sound that you can hear safely? If you listen to sounds above that limit, perhaps by blasting your music too enthusiastically, you probably you would change the answer to this question. What the faintest sound that you can hear, because you would damage your auditory system. So you probably can't answer. That was a difficult one to answer, but if you blast your music, damage your auditory system, the faintest sound that you can hear would probably change. So your threshold would change for the worse. So our thresholds for perception can change for a variety of reasons. So how do we measure that? So before you can know what the smallest amount of a given stimulus, is needed before we can detect a difference, we first need to know the amount of stimuli that is needed for us to even know that there is a stimulus there, period. So this is called a threshold. So a threshold is that dividing point between the energy level of a stimulus that do and do not have a detectable effect. So a threshold is that point in a stimulus strength where we first notice that something is there. Okay, so another key player in in the method of psychophysics and measuring thresholds, how do we do it, was a man named Ernest Weber. So Weber was a German anatomist and physiologist. He was really the first to formalize a study of the relationship between sensation and perception. Weber's most important findings involved the just noticeable difference, or the difference threshold. So he formalized, with an equation and figures that we'll look at coming up. He formalized the what is known as the just noticeable difference, or the difference threshold, which is the smallest detectable difference between two stimuli. So Weber's most important findings regarding the difference threshold involved judgments of lifted weights. So what Weber would do, he would ask people to lift one weight that would be called the standard. So the standard weight would be a weight that stayed the same over a series of trials. And then a comparison weight that differed from the standard weight by varying amounts. So what Weber would do, he increased that comparison weight by incremental amounts over a series of trials. So what he found was that the ability of a person to detect the difference between the standard weight and a comparison weight really depended on the weight of the standard. So when the standard weight was relatively light, people were much better at detecting a small difference. when they lifted the comparison weight. On the other hand, when the standard weight was heavier, people needed a bigger difference in weight before they could detect a change. So this is what we mean by the just noticeable difference. So it's the smallest detectable difference between two stimuli. And what Weber found was it depends on the starting point. So the just noticeable difference, it's not a value that you can just calculate and will be the same all the time. It depends on the starting point. So if you're starting with a light weight, you will be able to detect smaller differences. If you're starting with a heavier weight, you're going to need larger differences before you can notice a difference. So the just noticeable difference and what it is depends on the starting point. So this means that the just noticeable difference, it is not consistent for a given sense. So if you are lifting two objects, two different objects, you know, the smallest difference in weight between the two objects that you detect, can detect, going to depend on the starting point. So to give you kind of another example of this, so if we're talking about, weights again, and the smallest difference that we can detect, is it 1 ounce? Is it 2 ounces? Is it 6 ounces? It varies. So the just noticeable difference for heavier objects is greater than it is for lighter objects. So if something is heavy, it requires a large increase in weight for someone to notice that there has been a change. If something is light, it takes something is light. You can notice a difference, smaller difference. So if any of you lift weights, you may have experience with this. It's a lot easier to tell the difference between a 3-pound weight and a 5-pound weight than it is to tell the difference between a 23-pound weight and a 25-pound weight. In both cases, the difference is 2 pounds, but when the weight is heavier, it's difficult to notice a 2-pound difference. So Weber called the difference required for detecting this change in weight, he called it the just noticeable difference, or the JND. So like I said, we do have a graph coming up for this relationship between sensation and perception. Our sensation and our based on the intensity of the stimuli. So this relationship, known as the Weber-Fechner law. So the Weber-Fechner law, this refers to the size of the just noticeable difference, and that it is a constant proportion of the size of the original stimulus. Oh, just a second, my battery. Computer battery is. Okay, sorry about that. Okay, so the Weber-Fechner law, this is the size of the just noticeable difference and the fact that it is a constant proportion of the size of the original stimulus. So as the magnitude of a stimulus increases, as the stimulus intensity increases, the just noticeable difference becomes larger. Just 1 second, guys. Okay, so continuing on measuring threshold. So we looked at the just noticeable difference. Let's talk about the absolute threshold. So the absolute threshold is the lowest level of a stimulus that's needed for us to detect that it is there. So the smallest amount of energy needed to detect a stimulus. So the difference between the just noticeable difference and the absolute threshold is that the absolute threshold in detecting the presence of the absolute threshold is the absolute is basically we're talking about the difference between the just noticeable difference and the absolute threshold. We're talking about the presence of a stimulus versus a change in a stimulus. So the just noticeable difference, we're talking about a change. This is the smallest change before we can detect that there has been a change in stimulus intensity. For the absolute threshold, this is just the lowest level that's needed for us to detect the presence of a stimulus. So we're talking about the presence versus the change, with the absolute threshold being the presence of a stimulus, just noticeable difference being the change in a stimulus. Okay, so I do have this video. I have it posted on Moodle that kind of goes over, it does a little recap of thresholds and the Weber-Fechner law. Okay, so let's look at some of the methods that are used to get these thresholds. So how can we measure, something like the absolute threshold in a valid and reliable manner? So we've got these methods that will be the topic, one of the topics of your first lab assignment. So one of the methods that we have is the method of constant stimuli. So this method requires creating many stimuli with different intensities in order to find the tiniest one that can be detected. So if you've ever had a hearing test, you may have experienced this method. So for a hearing test, the doctor would have you report whether you could or could not hear a tone that was played to you over headphones. So in this test, intensities of all the tones would be relatively low, not too far above or below the intensity where your threshold would be expected to be. And the tones varying in intensity would then be presented randomly. The tones would be presented multiple times at each intensity. And then you just say, yes, I can hear them, or no, I cannot. So this multiple times piece is important because these subtle perceptual judgments are variable. The stimulus varies for physical reasons, but the observer varies as well. So our attention wavers and sensory systems fluctuate for all sorts of reasons. So as a result, one measure is never enough when you're talking about measuring thresholds. You need to repeat the measure over and over and over again, and then average the responses. Some experiments may require thousands of repetitions to establish a reliable threshold. So in the case of our auditory example, as the listener, you would report whether you heard the tone or not. You would always report hearing a tone that was relatively far above your threshold, and you would almost never report hearing a tone that was well below the threshold. In between those scenarios, however, you would be more likely to hear some tone intensities than not hear them. And you would hear other lower intensities only on a very few presentations. So in generally intensity at which a stimulus would be detected, 50% of the time would be chosen as your threshold. So you get a variety of stimulus levels being presented to you, and then you have the percentage of times that you reported that you heard it, and your threshold would be the time, would be the stimulus level where you detected the stimulus 50% of the time. So whatever we're talking, this is just an arbitrary stimulus level. It could be vision, it could be audition, it could be what have you. So this would be the threshold right in here that would be determined through the method of constant stimuli, where you were detecting it 50% of the time. So we also have the method of limits. So the method of constant stimuli, which we were just talking about, it's simple to use, but it can be inefficient in an experiment because much of the subject's time is spent with stimuli that are clearly well above or well below threshold to get that 50% point that is just detectable. So the method of constant stimuli, it requires many unnecessary trials to get those averages. A somewhat more efficient approach is the method of limits. So with this method, the experimenter begins with the same set of stimuli in our example, our example tones that vary. We're talking about tones here, so vary in intensity. But instead of random presentation with like what is done with the method of constant stimuli, for the method of limits, tones will be presented in order of either increasing or decreasing intensity. So when tones are presented in ascending order, so increasing from faintest to loudest, the listeners would be asked to report when they first hear the tone. So you've got a tone, starts off really quiet, probably inaudible, goes up and up and up and up and up to the point where you first say, yeah, I hear it. Now, if you're going to do it the other way, with a descending order, you then start with a tone that is clearly audible, and then you start decreasing, 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 decreasing to the point where the person says, nope, I can't hear it anymore. So with the method of limits, the data from an experiment like this, we've got an example here. So you can see here that there is some overshoot in judgments depending on whether the intensity is increasing or decreasing. So let's look here. So we've got, this is our trials, 1 through 8. This is our intensity. And the arrows indicate whether we've got decreasing or increasing intensities. So you can see here, so when we've got a decreasing intensity, the person's saying, yes, I hear it, yes, 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 and then you get down to here, and then they say, no, I don't hear it at 98. But what happens when you start with increasing intensity, they're saying, nope, can't hear it, nope, 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 nope. But you look here, no, they can't hear it. But yes, over here, they could hear 99. Same thing is happening over here in trial 3 when it's descending. You get a slightly different, so now this person is saying 98. Okay, I can hear it now. Go over to trial 4. Now we're increasing, and all of a sudden their threshold is here. So you can see that their threshold is kind of varying depending on whether you are starting with increasing, with decreasing, or increasing intensities. So basically, there is a tendency to report hearing lower intensities when you're using descending order. So you're more likely to hear lower intensities when you're using the descending order. In this case, if we take the intensity of 99 in column 1, the person reports they hear it, but if we look at column 2, when the intensity is increasing, they report that they didn't hear it. So to get an objective value for the threshold using the method of limits, what you can do is you can take the point for each of these sets, for each of these trials where the person goes from hearing it to not hearing it, and then you take the average of those points. So these are called crossover points. These dotted lines are called crossover points where the person goes from yes, hearing it to no, don't hear it. So the column, for 1, if we look for column 1 here, trial 1, it's 98.5, where they say that they hear it. The average is going to be 99 and 98. So for column 1, it's 98.5, which is the average of 99 and 98. So this can be done for multiple sets of ascending and descending intensities. And then the overall average of all of these crossover points can be taken where the listener, so the crossover points where the listeners shift from reporting the tone to not hearing the tone. And this average of those crossover points is taken to get the threshold. So if we look here, these are our crossover values. You take the average of those, and we get a threshold of 98.5. Okay. The last of these are our classical psychophysics methods. The last of these classical measures of thresholds is the method of adjustment. So this method is kind of just like the method of limits, except the subject is the one who steadily increases or decreases the intensity of the stimulus. So the method of adjustment, this may be the easiest method to understand because it's pretty similar to our day-to-day activities, like adjusting the volume on your phone. You turn it up or you turn it down to the point where you want it. So even though the method of adjustment, it's the easiest to understand, the method of adjustment is not usually used to measure thresholds. So it's easy to use. Why wouldn't it be used more often? Well, the method would be perfect if the threshold was consistent, even within one person, but it's not. So forget about finding a threshold, kind of between people, because the same person will adjust a dial to different places on different trials. And, measurements get even messier when you start trying to combine the data from multiple people. So the method of adjustment is, it's pretty unreliable because, when we're judging things, our judgments will change from trial to trial. Okay, so let's kind of forget about thresholds for a little bit, but at least forget about, absolute thresholds and different thresholds. So suppose we don't want to know necessarily, the thresholds, what the smallest amount of stimulus is that you can detect. Perhaps we want to know what the perceptual magnitude of a stimulus is. So suppose we wanted to know the magnitude of your perceptual experience. So for example, I could give you a light and ask you how much additional light you would need to make another light that looks half as bright. Now, though it may seem like an odd question, it is indeed answerable. I could give you a knob to adjust so that you could set the second light to appear twice as bright as the first. And you could do it. We don't even really need to get this fancy. We don't even need to give the observer a light to adjust. Surprisingly straightforward way to answer this question about the strength or size of a sensation is simply to ask observers to rate their experience. So for example, I could give you a series of, say, sugar solutions and ask you to assign numbers to each sample. So you can imagine that sweeter solutions have larger numbers. And if solution A is seen as being twice as sweet as solution B, the number assigned to A, the sweeter solution, should be twice the number assigned to B. So this method is called magnitude estimation, and it really just involves the participant assigning values based on the perceived magnitudes of the stimuli. Okay. So an important thing to keep in mind when we're talking about thresholds is that they are not absolute. So we do have a term called the absolute threshold, but thresholds are not absolute. In classical psychophysics, the subject's response to the stimulus is assumed to depend only on their sensitivity to the stimulus. So it is assumed to reflect that point in the stimulus level where our internal response shifts from low to high or high to low. But the problem with this assumption is that the responses that you get, are likely to reflect biases that the experimenter cannot know and can't control. Now, this problem is most severe when using something like the method of adjustment, and this is because the subject is controlling the intensity of the stimulus. So there's going to be a lot of variation in their responses. There's going to be a lot of room for error and inconsistency. But with any of the classical methods, you could get a different threshold in the same person by using a different method. So using the method of limits compared to using the method of constant stimuli or magnitude estimation. So you are guys, for your first lab assignment, you're going to be doing something we're going to call the DOT experiment. And basically, this is a little online interactive demo where you're going to adjust the intensity of a dot to the point where you can see it or not. And you're going to be using all three of the classical methods that we were just talking about. So method of limits, method of constant stimuli, and method of adjustment. And we can see, and you'll see when you do these little demonstrations, these little mini experiments on yourself, that the thresholds vary depending on the method used. So when I've done the dot experiment, this is the thresholds that I've gotten for myself. So when I use the method of limits, my threshold 5.08. When I do the dot experiment using the method of constant stimuli, my threshold is still 5.08, but when I use the method of adjustment, it drops all the way down to 3.88. So these are just my thresholds. So you can see here, you're going to get different thresholds, even in the same person, by using different methods to get these thresholds. So, so you can compare your thresholds to mine and compare your thresholds to the ones that you get for yourself for each of these methods. And you can see thresholds vary depending on the method used. So a reason why thresholds vary, can vary, in addition to the method used, another reason that they can vary is that we are always detecting a stimulus in the presence of noise. Even if you're sitting in the quietest place you can find, and you wear your best noise canceling headphones, you'll still find that you can still hear something. If you close your eyes in a dark room, you still probably can see something. Maybe it's a molted pattern of gray with the occasional brighter flashes. This is internal noise, the static in your nervous system. It's very difficult for us to do anything without some level of noise in the background in our mind, let alone background noise in the environment. So if you've ever tried to meditate, you are probably very aware of this background noise. This is why meditation is so difficult at first. So when you're doing a psychophysics experiment and you're trying to detect a faint sound or a flash of light, you must be able to detect it in the presence of that internal noise. So when you're detecting something that is very near your threshold, it will be hard to tell a real stimulus from the internal noise. When you're doing a psychophysics experiment, like the one in your lab assignment, you're going to be looking at a tiny dot appear. And you may find yourself looking, and if the dot is very faint, you'll find yourself saying, did I see that dot or did I imagine it? So this is a really good example of internal noise. So we have another method that addresses some of these factors that the classical psychophysics methods have issues with. So signal detection theory. So signal detection theory is a method that quantifies the response to a stimulus in the presence of noise. So signal detection theory accounts for, the presence of noise and also the presence of bias on the part of the observer. So signal detection theory acknowledges how important bias effects are by assuming that stimulus detection is a two-stage process, with the first stage being a purely sensory process where a given stimulus level will produce an internal response. And this will depend on both the intensity of the stimulus and the sensitivity of our sensory system. And the internal response is subject to internal noise. So the second stage for signal detection theory is a decision-making process. So it involves a decision-making process that compares the response to the stimuli to our internally set criterion. So this is called our response criterion. So let's just skip ahead. So the response criterion, this is where the criterion is met. Our criterion is basically our own internal decision line where we decide that a stimulus is present. And if it's not, we decide that it is not present if it doesn't meet our criterion. So this criterion can change, though, depending on many things. So our criterion can change based on, our level of arousal. Are we tired? Are we energized? Are we, distracted, thinking about something else? So the fact is that just because a stimulus is there doesn't mean we will detect it every time unless it is very well above our threshold. So other factors can affect our thresholds, our criterion. The criterion that is set by the observer is certainly one factor that's important here. So the response criterion, the response criterion is just how likely a person is to respond one way or the other. And this is basically set this is how sure you have to be before you say, yes, I saw the dot, or yes, I heard the noise. So the response criterion will change from person to person. So when you guys do your experiments for your first lab activity using the different psychophysics methods, I want you to make sure that you get your thresholds and compare them to mine. And you'll probably find that they're quite a bit different. Not because you can see all that much better than me, or I can see all that much better than you, but there's likely some variation that is due to physically being able to see the dot. Sure, that is true, but there's going to be some variation that is due to our differences, the differences in our individual response criterion. So that's the criterion, the threshold that each of us set. You can kind of think of this as the how much do I care criterion. So when you're trying to figure out if you should say yes or no, your response criterion will affect your threshold. So this is an internal threshold set by the observer. And if the stimulus that you're trying to detect is above your criterion, you'll say, yes, I saw it. If it's below, you'll say, no, I did not. But because the response criterion is set by you, this means that it will be different for everyone. You can think of it like being a yay-sayer or a nay-sayer. Some people want to be 100% sure that they saw that light or heard that sound before they say yes. Otherwise, they will say no. Other people are more free with their responses. They may say, well, I think I saw something. I'm pretty sure I did, so I'll say yes. But what happens in terms of thresholds is that the naysayer will have a lower threshold and the yaysayer will have a higher threshold. And this is not because they have different sensitivities or abilities to see or hear. It's simply due to the fact that one person is more likely to respond yes, so they may respond yes to something they did not actually detect. So the person, the yaysayer, is biased to say yes, and the naysayer is biased to say no, and this bias is going to influence their threshold. So an important point is that people say yes on trials when no sound is presented because they think there was a sound presented, not because they're lying. So when sounds are close to threshold, it's hard to tell whether there was a sound or not. So motivation, attention, and memory are factors that can also affect our criterion, our thresholds. So motivation, is one factor. Does the person really care if they get it right? So if you're a yay-sayer, you may not care as much as a naysayer who really wants to be sure they're right. And motivation can vary as well. So people often swear that they heard the phone ring when they're in the shower, even though they didn't. So that's, and we would expect that to be, that scenario to happen more. So hearing the shower in the phone, hearing the phone in the shower, you'd expect this to happen more often if you're expecting an important call. So the more likely the person would be to think the phone rang if they're expecting an important call. So if the call is really important, you're going to be more likely to interrupt your shower rather than miss the call. So motivation can be a factor, and other factors that influence a person's threshold are attention. Are they listening at all? Memory as well. Did the person forget what they were supposed to respond to? And you know what? This absolutely happens. And even if you're doing something really simple, like, just detecting the presence of a dot or the presence of a tone, you're possibly doing this on hundreds of trials. This is often the case in psychology studies. And the reality is that people may not be paying attention on every trial. Wow, right? Can't believe it. People aren't paying attention on hundreds of trials. It happens. Their mind may wander. They may forget what they're even responding to for a portion of the trials. These things happen. Realities of detecting stimuli. So a couple of key differences between signal detection theory and classical psychophysics methods is, one, with signal detection theory, only one stimulus intensity is presented. And another difference is that on some trials, no stimulus is presented at all. So this gives an idea of the individual person's likelihood of giving correct responses, of missing the stimulus, or of having a false alarm. So this is an important difference. We've got only one stimulus intensity presented, and in some trials we have no stimulus presented. So because signal detection theory, the methods of signal detection, present trials with no stimulus at all, this gives us 4 possible outcomes. So it allows responses to be broken down further instead of just looking at yes or no. So you can look at yes or no responses when the stimulus was either present or not. So this means we can have hits where the signal was present and the person responded, yes, I saw it. We can also have misses where the signal was present, but the person said no, they didn't detect it. And then we can also have false alarms where the response was yes. So the person said they heard it or they saw it, but there was indeed no stimulus. And then we can have correct rejections where there was no signal and the person responded, no, I didn't hear or see anything. So those are the different responses that we can get with signal detection theory methods. And it also, we can graph these as well to get an idea. So kind of 2 key graphs that are important for signal detection theory. We've got the distribution of signal plus noise and signal. Now, these distributions are assumed to follow a normal distribution, so that bell curve that you're probably familiar with seeing, which we'll see in the next slide. So we've got a distribution graph of the signal plus noise and signal, and then we've got another graph that we'll look at in a minute called the receiver operating characteristic curve, or the ROC curve for short. So let's first look at the distribution of signal and noise. Okay, so this is what we're looking at, and we're going to come back to this example of hearing a phone ringing when we're in the shower. Okay, so one way to deal with the issue of bias is to measure how often the person says yes or no on sound and no sound trials, for every sound level that you want to test. With signal detection theory, we get two distributions that capture the possible responses. So these graphs, these are theoretical. Each distribution is plotting the relative probability of an event. So we've got, so we're using our example of waiting for a phone call while you're in the shower. So now the phone ringing, that's our signal. So a ringing phone is a signal, and your perceptual task is to detect the signal, so the phone ringing, in the presence of noise. So what you're going to be hearing is a combination of the phone ringing and the shower. So the signal is being added to the noise, right? So we can imagine that we now have two we've got two distributions of responses. We've got a noise alone. We've got a noise alone distribution in the red, and we've got a signal plus noise in the blue. So that's going to be the phone ringing plus the noise. So let's suppose that the more response means that it sounds more like the phone is ringing. So sounds more like the phone is ringing or less like the phone is ringing. So your job is to decide whether it's time to jump out of the shower, interrupt your shower, and answer what could be the phone. So let's come back to our criterion as well. So say we're talked about our criterion being that point where we're willing to say, yes, we heard it, no, we don't. So that's our own individually determined point where we will jump out of the shower and get the phone. So the problem is that you have no way of knowing at any given moment whether you're hearing noise alone or whether you're hearing signal plus noise. The best you can do is decide on your response criterion. So you're going to decide on that point that's shown here with the black dotted line. So remember from a few slides back that the response criterion is an individual's tipping point between yes, they heard the sound, no, they didn't. So if you decide that it is above your response criterion, you're going to jump out of the shower, run dripping wet everywhere to find the phone. So if the level is below the criterion, you'll decide it's not a ring. You'll stay and continue your shower. So let's come back to, remember we had our four possible responses for signal detection theory. So we've got our hit, our miss, our false alarm, and our correct rejection. So we can kind of look at where they fall on these graphs. Okay, so you might, our four possible outcomes. So you might say no when there is no ring. So this right here, this is a correct rejection. So if you say no when there's no ring, that's a correct rejection. You are correctly deciding you didn't hear the phone and there was no sound. So there was no phone ringing and you said no. So that's a correct rejection. On the other side, we can also have are hits. So saying yes when there is a ring. So this is known as a hit, right? So in this case, you said yes and there was a sound. Now, there are two other possibilities of responses where these distributions overlap. So these are errors. These are our misses and our false alarms. So when the distributions for signal and signal plus noise overlap, we make errors. So the closer these distributions are, the more likely we are to make errors. The further they are apart, the more likely we are to be correct. So you can imagine, if we extended this graph and we pushed this blue distribution way over here, and we pushed this red distribution way over here, you would get no overlap, right? So you wouldn't get these errors that I've got highlighted in the middle here. So the further they are apart, the more likely we are to have hits and correct rejections. The closer they are, the more they overlap, the less able we are to detect the signal in the presence of the noise. Okay, so let's look at these errors, starting with the false alarm. So that's going to be right here. So this is the distribution of false alarms. So this is when we report a sound when there's nothing there. So you thought that you heard the phone, you jumped out, there was no phone. So this is a false alarm. The other error that we can make, the miss. So in this case, you missed the call because the phone rang and you didn't respond. You decided it was below your criterion, you didn't think you heard it. This is a miss. So our sensitivity to the phone ringing or the stimulus depends on the separation between the distributions. So like I was saying previously, like if you push these distributions really far apart and they're not overlapping, you are going to show high sensitivity and you're going to make few errors. So when there's greater separation between the distributions, our sensitivity is high and we make fewer errors. So let's look at how sensitive we are to the phone ringing. So our sensitivity is determined by how much the signal and the noise overlap. So we have here shown, shown here in these different distributions, these are different levels of sensitivity based on how much separation there is between the signal noise distribution and the signal distribution. So okay, so before we jump into this, I just want to address this term right here. This is called D prime. So D prime is just it's just the term for sensitivity, basically. So D is the sensitivity. I'm not going to ask you to calculate D or anything like that, but if these distributions are on top of each other, like in this case right here, this is going to mean that you can't distinguish between the signal and the noise from the noise alone. So this means that a false alarm is just as likely as a hit. So your performance is going to be at chance level, meaning that you are just guessing here. So you have no sensitivity. So when there's no sensitivity and the distributions are overlapping a lot, D prime is going to equal about 0. here. Now, this is just theoretical. You don't have to get tied up in the numbers, but just D means D equals 0. There's no separation. You're as likely to get a false alarm as you are likely to get a hit. So the separation of the distributions, this is captured by this measure called D prime, or just D. So what D prime is, it's just a standardized statistic. Don't get hung up on the value of D. Like I said, I'm not going to ask you to calculate it or even know what the number is that's associated with each of these levels. You don't need to know this is D0, this is D1, this is D4. You don't need to know that. Just know that D prime is just the standardized statistic for how far the distributions are. So if the distributions completely overlap, D will equal 0, and this means you have no ability to detect the signal. If D is intermediate, like in this middle one, this is moderate. You're gonna have moderate sensitivity. So you have some sensitivity, but your performance is not going to be perfect. You're still going to make some errors, right? If D is large, like it is in this case, this means that distinguishing the signal from the noise is easy. You have high sensitivity, and you're going to answer the phone every time it rings. So like I said, D prime, it's a measure of our ability to detect the signal. It's a measure of sensitivity. And it also gives us an idea of the distance between the distributions for the signal and signal plus noise. So if we know the number of hits to false alarms, we can calculate a sensitivity measure. So we know the number of hits, we know the number of false alarms, we can calculate D. So D is just a distance between the distribution for signal plus noise and the distribution for noise alone. The larger the D value, the greater our ability to detect the signal from the noise. The lower the D value, the less sensitivity we have, the more likely we are to make errors because we can't pull out the signal from the signal plus noise distribution. So making the decision to respond is about more than just how well we can distinguish the signal from the noise. We just talked about response criterions, that internal threshold that we set to be our tipping point between responding yes or responding no. So usually there is nothing that we can do to make the signal stand out more from the noise. And in these cases, you can't turn your shower down, you can't make it less noisy in there. But in these cases, all we can do is change our response criterion. So signal detection theory takes this into account as well. So let's look at this. Okay, so let's come back to our, detecting our phone call in the shower. So if we have, fixed D prime, in the sense that our distributions are fixed, we can't turn that phone volume up anymore to get over the noise. In this case, all we can do is shift your response criterion. So shift that internal criterion that tells you there's enough signal for you to respond. Now, this is going to change, right? So if you are waiting for a really important call, you will not want to miss any signals. So in this case, you may shift your response criterion over to the left. And you move it over to the left. And this means if you hear something that is even close to a ringing phone, you're going to get out of the shower and run to the phone. So this means you won't miss any calls, but you're going to have a lot of false alarms. But perhaps you are not waiting for an important phone call, and you don't want to be getting false alarms today. You're not waiting for an important phone call. You just want to enjoy your shower. So maybe then you move your response criterion to the right. Then you will miss more calls. But in both cases, your sensitivity stays the same. So your sensitivity is still the same. What is shifting is what you will accept as a signal, basically, depending on the context, depending on how important the phone call is. So, like I said, in both cases, D prime is the same. The sensitivity is the same. What has changed is your response criterion. What you will accept as justification for getting out of the shower. This is your response criterion. So, we will move on and look at our next graph. So we are looking at our distribution graphs that you can get with signal detection theory. Another key graph is this ROC curve. So what the ROC curve does is it plots hit rate as a function of false alarms. So we can plot the percentage of false alarms on the x-axis of a graph, and we can plot the hits on the y-axis and get this receiver operating characteristic curve. And this graph, it gives us, shows us the sensitivity of our responses. So the ROC curve shows how sensitive we are to picking up the signal in the presence of the noise. Okay, so what does it look like? Okay, so if you are guessing, your performance will look like this. This is chance, right? So this red diagonal, this is chance. So chance performance falls in the diagonal line, and this means you are just guessing. And you'll see here, the D associated with this is 0. So this, basically we have no sensitivity. And, you can imagine in this case, if we think about our signal and noise distributions, this line here, you would get this kind of response when you had a situation where the distributions were completely overlapped. You have no signal, no sensitivity, you're just guessing. So hopefully your data would look maybe more like this, this green line up here. So this means good performance. This shows, the green line shows a low percentage of false alarms. So we've got false alarms down here. So false alarms is low, hits are high. So we've got hits plotted here, we've got false alarms plotted here. So when the curve bows out this way, to the left, this means you got a lot of hits, not very many false alarms. The number of times that the phone rang and you heard it is high. If you're showing good performance on the ROC curve, good performance, your ROC curve will look like the green line. The curve will bow out to the top left corner. This means you have high sensitivity, your hit rate is high, your false alarm rate is low. So remember what we just said about the separation of the noise and signal distributions and those D values. So this impacts performance. So with a D value of 0, like in the red line here, this, like I said, this is where those distributions are overlapping completely and you get chance performance. With larger D values, you get better performance, like we have in the green line. So, you can see as D increases, the curve gets closer to that perfect performance line, which is the green one. So just to kind of recap what we said in what I was discussing in the graph, sensitivity, this is how well we can distinguish the signal from the noise. And if D is large, those distributions show less overlap and our sensitivity increases, which is what we have in the green line here. This is high sensitivity. So D is large, the distributions are far apart, we've got high sensitivity, we can we're getting many hits and not a lot of false alarms. So for signal detection theory, basically consistent thresholds don't exist. So with signal detection theory, you're not trying to find that one value where everybody can detect something, or even where one person can detect something all the time. Signal detection theory is not trying to find consistent thresholds. The concept of a threshold really ignores the decision-making process of the observer. And this decision-making process, this happens every time we're detecting a stimulus. So for signal detection theory, there is no threshold. Signal detection theory takes into account the fact that people are making decisions as they make sensory discriminations. So when we attempt to separate a signal change from the background, we may guess, we have biases in our judgment, we become more or less vigilant during the judging process. So there is no consistent threshold for signal detection theory. So the good thing about signal detection theory is that it takes into account the fact that people are making decisions. It takes into account that we're making decisions. Sometimes we're guessing. Sometimes we have biases. We're waiting for an important phone call, or we are not waiting for an important phone call. And this is, going to, change how much attention we're paying to the signal. So all of these things are going to affect whether or not we detect the signal. Okay, so that wraps it up for this pre-recording, or this makeup recording. We'll pick up next class. We'll perhaps just talk about some of the methods for measuring sensory systems, like physiological methods, neurophysiological recordings, EEG, MRI. Okay, so this is all you guys need for your lab, right till this point right here, up till signal detection theory. And I will see you for any one of the times I've set aside for going over the course outline. And if you don't attend those, I will see you on Thursday with reliable internet. Okay, thanks guys.